Representations of functions as power series. Let's revisit the geometric series. We know that the series 1 plus x squared plus x cubed plus etc., which is equal to the summation of x to the n equals 0 to infinity, is a geometric series. The first term is 1 and the common ratio is x. So we know that the first term a is equal to 1, the common ratio r is equal to x, and the sum of the series we know is a divided by 1 minus r, which in this case is 1 divided by 1 minus x. And of course, this is only true if the absolute value of the common ratio, which is x, is less than 1. So we know that this series has a sum equal to the function 1 divided by 1 minus x, as long as x is a number in between 1 and negative 1. So what we say here is that this power series represents the function 1 over 1 minus x as long as x is a number in this domain. To help you see that this is the case, I have the function 1 over 1 minus x graphed here in red. And then I have a few of the partial sums of this power series. The first sum that I have is y equals 1 plus x, which is this line right here. And then I have y equals 1 plus x squared, which is this parabola here. And then we have 1 plus x squared plus x cubed. And finally, 1 plus x squared plus x cubed plus x to the fourth. So each time here you should notice that I'm just adding one additional term of this infinite series. And what I want you to see is that the graphs of these partial sums gets closer to the graph of the function when I add more terms. So what I'm trying to get you to see here is that if we do the sum from 0 to infinity, this graph would match up perfectly with the graph of the function in between x equals negative 1 and positive 1. So what we can see here is that on certain domains, power series can approximate functions. And this is a very useful trait. So the question is, how do we find a power series representation for a function? Let's take a look at an example. So here we want to express the function 1 over 1 plus x squared as the sum of a power series, and also find the interval of convergence. So let's remember that 1 divided by 1 minus x is the sum n equals 0 to infinity of x to the n. And this is true if x is a number between 1 and negative 1. And again, this is our geometric series. So we have the function f of x is equal to 1 divided by 1 plus x squared. I want you to notice that this function is similar to this function. Not exactly the same, but they have some similar traits. They're both fractions, for example. They both have a 1 in the numerator, and they both have a 1 in the denominator, and this one says minus x, and this one says plus x squared. So allow me for a moment to just rewrite this function as 1 divided by 1 minus negative x squared. In doing this, we can see that this function here will become this function if I simply replace x with negative x squared. But if I replace x here with negative x squared, that would be the same as replacing the x in here with a negative x squared. And that's one way we can get a power series representation for a function, is we can get it by substitution into a known power series for another function. So let's go ahead and make that substitution. The series will become the sum n equals 0 to infinity of negative x squared quantity to the n. And this is the same as the sum n equals 0 to infinity of negative 1 to the n times x squared to the n. And this finally can be written as the sum of negative 1 to the n x to the 2n power just by using a property of exponents which allows us to multiply these powers together. So in the end here, you can see that the function 1 over 1 plus x squared has a power series representation, summation n equals 0 to infinity, negative 1 to the n, x to the 2n. And if we write out some of the terms of this series, just by letting n equal 0, for example, we will get 1. Let n equal 1, we will get negative x squared. Let n equal 2, we will get positive x to the 4th. N equals 3, negative x to the 6th, etc. So then the only other question is, on what values of x, or for what values of x, does this converge? Well, we know up here with the geometric series, it converges when x is between 1 and negative 1. But remember, we substituted negative x squared in for x here and also here. And so we're going to do the same thing here. We're going to substitute negative x in there, and that's going to tell us that I said negative x. I meant to say we're going to substitute negative x squared in for there. And that tells us that negative x squared is a number between 1 and negative 1. And that would only happen if x squared is a number between 1 and negative 1. And that's going to happen if x is a number in between 1 and negative 1. So coincidentally, it has the same interval of convergence. So one way to get a power series representation for a function is just by making a substitution. In the second example, it's essentially the same thing. We just have a different function. So let's remind ourselves of the geometric series. And then now we're going to take our function, which I'm going to call f of x is 1 over x plus 2. And we need to try to make this look like this. So first thing I'm going to do here is just switch it around to say 1 divided by 2 plus x. And then we really need this 2 here to be a 1. So how do we do that? Well, one way to do it is we simply factor out a 2. When I pull a 2 out of 2, I get a 1. And then when I pull a 2 out of x, I'm going to get x divided by 2. And this can be rewritten as 1/2 times 1 divided by 1. And then one other thing I need to do, I need to change this to a negative sign. So I'm going to write minus and then negative x over 2. And so you should see here that this looks very much like this. The only difference is instead of having an x here, I have negative x divided by 2, which means I'm going to plug negative x divided by 2 in for here, and I'm also going to plug negative x divided by 2 into here. So to get the series, don't forget the 1/2. So we have 1/2 times the summation n equals 0 to infinity, and then negative x over 2 is going to replace x here. And so that is negative x over 2 quantity to the n. And then we're going to go ahead and simplify this. And so we have the summation n equals 0 to infinity. Let me bring the 1/2 inside. And then here, when we have negative x over 2 to the n power, we're going to raise negative 1 to the n power, x to the n power, and also 2 to the n power. And so when we do all that, we will have negative 1 to the n, x to the n, divided by 2 to the n. And now we're just going to combine as much things as we can here. So we've got negative 1 to the n divided by, now in the denominator I have 2 times 2 to the n. So that's 2 to the 1 times 2 to the n, and that is the same as 2 to the n plus 1. And then times x to the n. And this is our power series representation of our function. Now, for what values of x does it converge? Well, again, to figure this out, we're just going to take negative x over 2 and replace x here. So in doing that, we will have negative 1 less than negative x over 2 less than 1. Well, this means that x over 2 would have to be in between negative 1 and positive 1. And then if I just multiply everything by 2, you'll see that we get a slightly different interval of convergence here. So the function 1 over x plus 2 is equal to the power series representation, summation negative 1 to the n over 2 to the n plus 1 times x to the n for the values of x between negative 2 and positive 2. And one thing you could do here to verify this is you could graph a few members of this power series to see if it looks approximately the same as 1 divided by x plus 2. And you could do this using software. In the next example, we're asked to find a power series representation of the function x cubed divided by x plus 2. Now, what I did here is I brought in the result from the previous example because I want you to see that this function here is related to the function here. Particularly, if I have the function x cubed over x plus 2, we know that we can write this as x cubed times 1 over x plus 2. And we know the power series representation for that. So this would be equal to x cubed multiplied by the sum, n equals 0 to infinity, negative 1 to the n over 2 to the n plus 1 times x to the n. Now here's the important part. This is the variable x. In the summation, the variable is n. So because this does not have an n, it is like a constant, and it can be freely taken into the sum or out of the sum, just depending on what you need to do. So in this case, what I'm going to do is bring it back into the sum. And this will allow me to combine those x's there. And so we'll end up with the sum n equals 0 to infinity, negative 1 to the n over 2 to the n plus 1 times x to the n plus 3. And so now we have a power series representation for our function here. And one nice thing about this power series representation, since we got it by simply multiplying this series by something, it doesn't change the interval of convergence at all. So this is still valid on the same interval. Now let's shift our focus to a theorem. This theorem tells us that if we have a power series that has a radius of convergence r that is positive, then the function defined by that power series is differentiable and also continuous on the same interval. And we can get the power series for the derivative of the function by taking the derivative of each term. And we can get the antiderivative of the function represented by the power series by taking the antiderivative of each term of the power series. So to put it simply, when you have a function represented by a power series, the derivative of that function can be represented by the derivative of the power series. How do we take the derivative of the power series? Term by term. So just notice here that if you were taking the derivative of this with respect to x, you would use the power rule. The exponent n would come down and you would subtract 1 from that power. And that is exactly what happens here. You can see that they brought the n down in front and we subtracted 1 from that power. Same thing is true for the antiderivative. So how would I take the antiderivative of a term like this? Well, you take the power and you add 1 to it, so you get n plus 1, and then you divide by that power. So you can find power series for the derivative and antiderivative of a known function by taking the derivative or antiderivative of the power series. This is an extraordinarily important theorem in analysis. Let's take a look at an example. Here we wish to express the function 1 over 1 minus x to the second power as a power series. Now let's remind ourselves of the geometric series. And I want you to notice that you really can't get this series here by making a substitution. So the function in question here is 1 over 1 minus x quantity squared, right? So if it was just x that was being squared, we could just make a substitution. But because it's the whole thing, this is not going to work here. So let's think about how do you get from a function like this to a function like this? And let me pause for a second here to talk about derivatives. We know that if we have a function f of x equals 1 over x, that we can express that function as x to the negative 1. And then we know the derivative of that function would be negative 1x to the negative 2, which can be rewritten as negative 1 divided by x squared. Let's do the second derivative. In the second derivative, we would just simply take the derivative of this, which is going to give us positive 2x to the negative 3, which would be 2 divided by x cubed. And I'll do one more derivative just to make sure you understand the pattern here. But it's going to be negative 6x to the negative 4, which is negative 6 divided by x to the 4th. So what's the takeaway from this? Well, the takeaway is that when you have x to the first power in the denominator, every time you take a derivative, it increases the power of x in the denominator by 1. So how does that relate to what we're doing here? Well, think about 1 minus x here as being 1 minus x to the first power. So in a way, you can think of this function as 1 minus x quantity to the negative 1. So what would you get if you took the derivative of that function? Well, you know what you would get. You would get negative 1, 1 minus x to the negative 2, and then the chain rule says you also have to multiply by the derivative of the inside, which is negative 1. And this is equal to 1 divided by 1 minus x to the second power, right? Because the negative cancels with the negative here. We drop this down to the denominator, make the exponent positive, and there it is. So the derivative of this function is actually exactly equal to the function that we're trying to represent as a power series. So what does that mean? Well, it means that the representation of this function as a power series will be the derivative of the power series. Okay, so let's take it from the top now that we have an idea of what we're going to do. So from our discussion here, we know that if we take the derivative of this function, we are going to get this function. So basically what I'm doing is I'm taking my geometric series and I'm going to take the derivative of the left-hand side, and that is going to be equal to the derivative of the right-hand side. So what is the derivative of 1 over 1 minus x? Well, again, we just did that, and we know that it's 1 divided by 1 minus x quantity squared. And that is going to be equal to the derivative of the right-hand side. Now, when you take a derivative of your power series here, the key step is that you are taking the sum of the derivative of x to the n. So you're basically bringing your derivative to the inside of the sum. And this is going to give us the sum of, what is the derivative of x to the n? Well, it is nx to the n minus 1. And now here's the thing. Normally we would say n equals 0 to infinity, but notice when you plug in 0 now, you actually get 0. So there is no reason to start at n equals 0. We're going to start at n equals 1 instead. Now another nice thing is we know that the original interval of convergence for your geometric series is x has to be between -1 and +1. When you take the derivative of a function to get a power series, it is going to have the same interval of convergence. The only thing that might change is that you might include an endpoint where an endpoint wasn't included before. So you might have to test your endpoints to see if they are also a part of that interval of convergence. In this case, I will save you the time there and tell you that if you plug in -1 or +1 here, it is going to diverge, and so we don't have to check our endpoints here. So we can find a power series by substitution, and we can also sometimes find a power series by taking a derivative. Next, let's find a power series representation for the function natural log of 1 plus x and its radius of convergence. And once again, we're going to need the geometric series to do this. So here's our geometric series, and let's remind ourselves that if we had the function 1 over 1 plus x, that could be written as 1 over 1 minus -x, and I could get the power series for this function by simply substituting -x into our geometric series. So this will be the sum n equals 0 to infinity, -x quantity to the n power. And this can be written as the sum of -1 to the n, x to the n, and it will have the same interval of convergence. Now, why am I talking about 1 divided by 1 plus x? We're trying to find the power series for the function natural log of 1 plus x. Well, it goes back to this. We know the integral of 1 over x dx is the natural log of the absolute value of x. And we also know the integral of 1 over 1 plus x dx is the natural log of the absolute value of 1 plus x. And you can get this by making a simple u substitution here. Okay? So the thought process is I need the power series for 1 over 1 plus x so that I can take the antiderivative to get the natural log function, and then I'll find the power series by simply taking the antiderivative here. So basically what's happening is we have our power series for 1 over 1 plus x, and we are going to take the antiderivative of the left side here, and that is going to equal the antiderivative of the right side. Now, as we just mentioned, the antiderivative of 1 over 1 plus x is the natural log of the absolute value of 1 plus x. And now on the other side, I'm going to take the integral and move it to the inside here. So I'm going to have the summation n equals 0 to infinity. -1 to the n is a constant, and we're going to multiply that by the integral of x to the n dx. And this, of course, we know is x to the n plus 1 divided by n plus 1. So we get the sum, -1 to the n, times x to the n plus 1 divided by n plus 1. And then don't forget plus a constant of integration. And we also know that it has the same interval of convergence. Okay, now we will have to check our endpoints to see if they converge or if the series converges there as well, but we'll do that in a minute. So first of all, let's just notice that the natural log of the absolute value of 1 plus x, we don't need the absolute value here because if x is a number strictly in between -1 and +1, this will never be a negative number. So we've got the natural log is equal to the sum of -1 to the n over n plus 1 times x to the n plus 1 plus c. Now, if I let x equal 0, which I can certainly do because that is in our interval of convergence, what we get on the left-hand side is the natural log of 1 plus 0, which is the natural log of 1, which is 0. And on the right-hand side, if I plug in x equals 0, this whole series becomes 0, because when you plug in 0 for x, everything becomes 0. So we can figure out that c is 0. Okay, So now that we know c is 0, we can plug that in, and we have our function, natural log of 1 plus x, is the sum of negative 1 to the n over n plus 1 times x to the n plus 1. Now let's get back to our interval of convergence. What do we get if we let x equal negative 1? Well, if you plug in negative 1 for x, you actually get the sum of negative 1 to the n times negative 1 to the n plus 1 over n plus 1. And this is going to be the sum of negative 1 to the 2n plus 1, right? All I'm doing here is adding those powers together. But 2n plus 1 is always an odd number for any integer n. So this becomes the sum n equals 0 to infinity of negative 1 over n plus 1, right? Because negative 1 raised to an odd power is negative 1. And this diverges. It diverges because this is the negative harmonic series. It's the harmonic series where every term is negative. So we will not be including negative 1 in our interval. What if x equals positive 1? Well, if we plug in positive 1 into our series here, we're going to get the sum n equals 0 to infinity, negative 1 to the n times 1 to the n plus 1 over n plus 1. 1 to the n plus 1 is simply 1. So we have negative 1 to the n over n plus 1. And this converges. It converges because this is the alternating harmonic series, and it converges by the alternating series test. So since it converges at x equals 1, we need to include that in our interval of convergence. So I come back to our answer here. We have the function and its power series representation, and the interval of convergence here is going to be all numbers in between 1 and negative 1, including 1. Next, we want to find the power series representation for the function inverse tangent of x. So you got to think a little bit. You got to think, what is inverse tangent of x? How can I express inverse tangent of x in relation to what we know about the geometric power series? Well, let's see. Do we remember that inverse tangent of x is the antiderivative of 1 over 1 plus x squared? Yes, this is true, isn't it? Well, that's good news, because 1 over 1 plus x squared is a power series that we found earlier in this video. So from example 1, we know that 1 over 1 plus x squared is equal to the power series summation negative 1 to the n, x to the 2n. And so inverse tangent of x is equal to the antiderivative of 1 over 1 plus x squared, and that is going to equal the antiderivative of the power series that represents 1 over 1 plus x squared, which is this power series here. And then we know that we can bring that integral inside of the power series to act upon x to the 2n. And when we do that, the antiderivative of x to the 2n is x to the 2n plus 1 divided by 2n plus 1 plus c. And so now we have the inverse tangent of x is equal to the power series summation negative 1 to the n times x to the 2n plus 1 divided by 2n plus 1 plus c. Now let's figure out the value for c. If we let x equal 0, we know inverse tangent of 0 is 0. And if we let x equal 0 here, all of these terms become 0. So basically we know that c must be 0. So we can get rid of the plus c here. And we know that this series will converge on the interval -1 to +1. But then we have the question, does it converge at the endpoints? Well, let's check. If we plug in x equals -1, the series becomes the sum -1 to the n, -1 to the 2n plus 1 over 2n plus 1, which is equal to the sum of -1 to the 3n plus 1. Now you have to think, what is 3n plus 1? Well, 3 times n alternates between being an odd number and an even number. And so when you add 1 to it, it's also going to alternate between even and odd. So believe it or not, this is an alternating series. And so it converges by the alternating series test. Now I'm not going to run the test here, but remember to run the alternating series test, you have to show that the terms 1 over 2n plus 1 are decreasing and also the limit goes to 0. And that's pretty easy to show here. What if x equals +1? Well, if you plug in +1 for x, you get the sum -1 to the n over 2n plus 1, because when you put 1 in here, you just get 1. And this is also a converging series by the alternating series test. So in this case, both endpoints converge. And so we are going to include both endpoints. So our final answer is this power series on this interval of convergence. Our final example is an example of why this is so useful. So first, we want to evaluate the integral of 1 divided by 1 plus x to the 7th as a power series. So we are taking the integral of 1 over 1 plus x to the 7th dx. So the first thing we need to do is find a power series for 1 over 1 plus x to the 7th. So again, we know that 1 over 1 minus x is the sum of x to the n. Therefore, 1 over 1 plus x to the 7th, we can rewrite this as 1 over 1 minus negative x to the 7th. And that is going to be the power series n equals 0 to infinity of negative x to the 7th to the n. And that will be -1 to the n times x to the 7n. And this will converge on the same interval, -1 to +1. So if the power series for 1 over 1 plus x to the 7th is this series here, then the antiderivative of that function will be the antiderivative of this power series. And so this is equal to the integral of the sum of that power series. And then we know that we can bring the integral inside of the sum and just take the antiderivative of x to the 7n. And this is going to give us the sum n equals 0 to infinity, -1 to the n times x to the 7n plus 1 divided by 7n plus 1 plus c. And this is the power series for the antiderivative. Now, in part B, it says use part A to approximate the definite integral from 0 to 0.5 of the same function. So if I bring in limits now, 0 and 0.5, we know the antiderivative of this is the same. So let's go ahead and bring that over. And we can drop the plus c because we now have a definite integral. And so now we just need to evaluate this at the limits. And of course, to evaluate, you use the fundamental theorem of calculus, which means you're going to plug in 0.5 for x minus, and then plug in 0 for x. Well, when you plug in 0, you get nothing. So all you have to do is plug in 0.5. And so this becomes the sum n equals 0 to infinity, negative 1 to the n, times 0.5 to the 7n plus 1 divided by 7n plus 1. All right, so now we have a power series that represents this definite integral, but they want us to approximate this correct to within 10 to the negative 7. So we want the error to be less than 10 to the negative 7, which is 0.000001. So how do we do that? Well, notice that this series is an alternating series, and it converges by the alternating series test. And we know that in an alternating series, the absolute value of the error is always less than or equal to the n plus 1 term. Well, the n plus 1 term is this term here with n being substituted with n plus 1. So it is 0.5 to the 7 times n plus 1 over 7 times n plus 1 plus 1. And so that n plus 1 term is 0.5 to the power 7n plus 8 divided by 7n plus 8. And we want that to be less than 0.000001. So what we need to do now is just observe what is the smallest number n for which this is true. And I will just tell you here that if you let n equal 2, this an plus 1 is going to be 0.5 to the 22 divided by 22, and this number is less than 0.000001. So n equals 2 is the answer, which means to approximate this integral, we have to add up this series here, from n equals 0 to 2. And so when we do that, here's what we get. So the approximate value of this integral is 0.4995514. It's quite extraordinary if you think about it, because we don't know the antiderivative of this function. And yet, because we have a power series representation for that function, we can take the antiderivative of that power series and then plug in the limits of integration and then use the alternating series estimation theorem, which tells us how many terms we need to add up. And in the end, we only had to add up 3 terms, right? N equals 0, n equals 1, n equals 2. And that gave us a 6 decimal place approximation, which is quite extraordinary. And that concludes this video lesson.